So arranging objects. Now this is slightly different to the fundamental counting principle because if we were to arrange the letters H, E, L, P, what ends up happening is when we choose the first letter, we don't have four letters to choose from for the next three letters. Okay, so the number of selections changes after each selection. So slightly different than um, using the fundamental counting principle. Now we could list these out, and there's not that many that we couldn't list out. We could do H, E, L, P. You could do H, E, P, L, H, and then we could maybe go with L, E, P, H, L, P, E, H, P, and then E, L, H, P, L, E. And this would represent all the possibilities that start with H. And then we could do that for all the possibilities that start with E, with L, P, and just make a giant list. And now we know that there's some symmetry to this. So if there's 6 here and 4 different letters we can start with, there's probably 24 in total. But this is a tedious way to count this out by listing out. It's very reliable, but it's very tedious. So we want a different way to count this more efficiently. And we're going to use some multiplying method that is going to relate to the fundamental counting principle. So we're going to just ask ourselves, well, there are 4 letters here that we have to choose. Make a better square here. So there's 4 letters that we're going to choose. And in the first selection, there's 4 different letters we can put into here. Now, once we choose one letter, there's only 3 letters that we can put into the next slot. And we can combine these because there are groups, we can do this in groups. So we can combine this with multiplication. And then we can move on to the third letter. If we've already chosen 2 letters, there's only 2 left to choose from. And then we can combine it with multiplication. And then the last letter, there's no choice. There's only 1 left to choose from. So there's really no choice. And when we multiply this all out, we end up with the 24 different possibilities of combinations. And we could do this using this descending multiplication strategy. Now, this descending multiplication actually has a function that does it for us. It's called factorial. And it's this exclamation mark. This is a mathematical function. It's called factorial. And what it does is when we input a number, it will multiply that number all the way down to 1. And then combine that all to get an answer. So 5 factorial, for example, if we multiply 5 times 4 times 3 times 2, 5 factorial works out to be 120. And we can do this on our calculator. Our calculator has this function built in. And we can generalize this as n factorial, is we're just going to start with the number n, and then we're going to multiply all the way down successively until we hit 1. And that's how factorial can be applied, and this is how we generalize it algebraically, writing it like this: n times n minus 1 times n minus 2, etc., all the way down to times 1. And so factorial happens to be a very powerful function, and it grows very, very quickly. So if you actually tried this on your calculator, you cannot do factorials for very big numbers because it will overload your calculator capacity very quickly. So for example, your calculator generally can store up to 100 digits. Okay, and factorial will overload that. If you do 100 factorial, you'll have more than 100-digit number. It's too big for your calculator to be able to handle. Okay, so factorial grows very quickly. So we can use this factorial for all these descending multiplication problems. Another example here would be if we had a boat. Okay, so we have a boat and they're all in a line. We're going to seat people in a line in a boat. So we got our first seat at the front. We got our second seat behind, and they're all in a row, so that's the third seat right behind the second, the fourth seat right behind the third, the fifth seat right behind the fourth. So we have 1, 2, 3, 4, 5. Oh, there's 6. So there's 6 seats. So there's 6 seats on this boat, and we have different people. We could put Jack in here. We could put Sally in here first. Anyone could be at the very front. So the number of choices for the front person, there's really 6 possibilities. And then once we've chosen the first person, there's only 5 left to put in the second seat. And we can combine the combinations with multiplication. Get to the third seat, there's 4 people. We can combine it with multiplication. There's only 3 left for this seat, 2 left for this seat. And once we have 5 people seated, the last person in the boat has no choice. They have to take that last seat. And so this can be calculated with 6 times 5 times 4 times 3 times 2 times 1. Or, in other words, we can use 6 factorial on our calculator. Now, again, we can just multiply this out, but 6 factorial is very efficient. We can just type in hit 2 buttons on our calculator, and it will calculate that product very quickly, and it gives us 720. Now, this descending multiplication is useful because we can actually have the same 6 rowers, and instead of 6 seats in a boat, we're going to take away a seat. So that means one person is going to be left out of the boat. And we're going to have our 5 seats in our boat, and then we're going to have one person have to sit on the sideline here. Okay, so how many ways are there to do this? I have use 5 in a 5-person boat. So this is out of the 6 rowers, there's 6 possibilities to sit at the front, 5 in behind, 4 in behind that, times 3 times 2. And the number of ways that this could be done is going to be 720. Now, this happens to be the same as the first problem. And why is that the case? Well, once you fit 5 people in, there actually is no choice for the last person. So basically, once you fit the first 5 in, you've got all the different possibilities accounted for. Because that last possibility, 1 here, that one person that you leave behind, there's no choice. Okay, so we don't get different combinations for that.